In part one of this presentation, we ended on an example of a 2-chiral center molecule and a complete resolution of all 4 individual isomers from that molecule using chiral SFC. Let's take a look at another example. Here's a 2-stereocenter sample. In this case, we've got a relative abundance of the 2 enantiomer pairs in our achiral UPLC run. And again, we're leveraging UPLC's fast chromatographic development speed and its high peak capacity to see those, to assign individual retention times to those enantiomer pairs. But we see that the area of those peaks is roughly 50-50, and we can predict that the relative abundance of the individual isomers should be about 25% each. Let's take a look at the chiral chromatograms. These again are gradient screening chromatograms meant to show us where stationary phase interaction is. We get some complete resolution to some degree of all 4 of the peaks in chromatogram 6 here, but it's not sufficient resolution to give us high yield at preparative chromatography. So what we're going to do is we're going to look at chromatogram 5 as our chromatographic method that we're going to scale up to prep. And what we expect from this is that fraction 1 and fraction 3 will produce individual isomers, but fraction 2 will have 2 isomers in it. Fraction 2 may have a pair of diastereomers, or it may have a pair of enantiomers. We don't know. But we can use the UPLC chromatogram to sort this out. So here's our original sample UPLC showing both pairs of enantiomers, and we can assign F1 as one of the enantiomers from this peak, and F3 as one of the enantiomers from this peak. F2 contains not a pair of enantiomers, but a pair of diastereomers. So we're getting quite a bit of information out of layering these 2 types of chromatography together. This becomes important when you start to look at 3-stereocenter compounds. Here's a chiral screening chromatogram from an attempt to separate all 8 isomers from a molecule that has 3 stereocenters. In fact, we can get individual bands out of about 7 of them, but we're going to end up, when we take this to prep, with a long stacking time, some problematic small impurities here and possibly in the middle of the chromatogram someplace, partial recovery of the peaks because we've got incomplete resolution, and worst of all, 7 fractions, not 8. One of those fractions must contain 2 enantiomers, 2 isomers, not necessarily enantiomeric of each other, but 2 isomers. If that's screening of those 7 samples that we've produced produces a separation, we're complete at that point. But if it doesn't, if that screening is negative, now we've got to go back to the chemist and say, we only got 7 fractions. One of them probably contains 2 isomers, but we don't know which one. It's an unsatisfactory degree of completion of the project. So in fact, what we do is we leverage that UPLC separation that allows us to get another layer of information, and that makes it less important to what degree we separate all of the enantiomers in a single screening run. So you can see that 2 and 8 maybe produce a little bit better resolution than the one that we've chosen here, which is chromatographic method 4. But method 4 we've chosen because it's got a lesser retention time, which means faster processing. It's got a very sharp band shape. That indicates to me potential loading and processing efficiency is pretty high. So we'll go ahead with method 4. And when we scale to preparative chromatography with method 4, we end up with 4 fractions. And again, using the original sample's UPLC results here, which assign unique retention times to these pairs of enantiomers, we've assigned them arbitrary names now, D1 and D2 and D7 and D8. represent diastereomer 1, 2, 3, 4, etc., etc. But when we look at the fractions that we collect here, we can see immediately that fraction 1 and 4 are complete. We can see fraction 1 is complete, for example, because there is a peak in fraction 1 that has the same retention time as a similar peak in fraction 2. We've resolved fraction 1 and 2 in the original chromatogram over here, and that means that these are two different individual isomers. So at this point, we simply have to go back and find a method for fractions 2 and 3 that will allow us to resolve these 4 peaks in one case and 2 peaks in another. The other thing we know at this point is that all 4 of these peaks in fraction 2 are diastereomeric to one another. There's no remaining pair of enantiomers because the other enantiomer at each of these retention times ends up in another fraction. So that gives us some information we can use. And the relative abundances of those 4 peaks are clear from the chromatogram. So we have a lot of information that'll help us set up screening runs. Moreover, our initial screening run produced a number of phase interactions that we didn't leverage in this final separation, so we can go back to those and see if any of those work. And in fact, that's exactly what we found. We had an SFC method where we'd identified a stationary phase interaction in the first screening run, and another one that worked with fraction 3. We were able to scale both of those to preparative scale and deliver pure individual isomers. Our final results are nicely expressed in this fraction tree. What you can see is that in no case did we need more than 2 chromatographic methods. In the first case, method 1 and then method 2. And then in the second case, method 1 and then method 3 to produce pure individual isomers. We've got, based on HPLC retention time, we've got assignments of the pair relationships between fractions, knowing, for example, that fraction 1 and fraction 6 contain an enantiomer pair. We've got certainty of completion. In other words, each one of these fractions, we know when we're done. We know we're not done with fraction 2 and fraction 3, and we have to go further. We know we are done once we've got all of these individual fractions. The time necessary to do this is no more than a few hours for each individual small-scale sample, and that means that a chemist can work through 3 chiral center samples in one day. That's a pretty high productivity rate for a complex separation like this.